Thank you so much, Valeria, for introducing me. So today I'm going to talk about our recent work, directed cyclic graph for causal discovery from multivariate functional data. So this is a joint. This is a joint work with two other fantastic individuals. I think Yang has joined us over Zoom, and Dr. Wong is over here. And they are my two advisors. So this is a brief outline of my talk. So I'll begin with developing some background of why we need causality, and I'll describe some causal nomenclatures that would be used throughout this talk. I'll then proceed to describe the main motivation of my talk. It's the multivariate functional data. I'll define what is multivariate functional data. I'll describe a bit about what are the challenges to do causal discovery from multivariate functional data. I'll give a motivating example, and then I'll proceed to give a brief introduction of our proposed method. We have simulation studies and real data analysis to back up our method, and we'll end with some key takeaways. So let's begin with why we need causality. So this is as you can see, this is a screenshot of an Amazon web page. It's my personal Amazon account. You can see my name, and you can also see Snigdha's name. We are poor graduate students, so we share the same Prime account. And this is like coming to the talk. I searched for like buying laptop bags. So what the Amazon recommendation system did, it also recommended to buy me a laptop. So this is pretty weird, right? So I want to buy a laptop bag, but it's suggesting me to buy a laptop. While the vice versa would be more appropriate. If I want to buy a laptop, then I might want to buy a laptop bag. But so if you go and check Amazon database you can find that there are significant association between these two things like laptop bags and laptops. But here we are clearly ignoring the underlying causal direction that we have from buying laptops to laptop bags. So this is one of the, we need causality to understand this. This is one of my examples. Another example is, this is a synthetically generated data set. So in this two scatter plots, in the x-axis, we have activity of two genes, gene A and gene B. And in the y-axis, I have some phenotypic expression. It can be flowering or anything, any example of phenotypic expression. So if I ask you a statistical question, suppose I ask you a statistical question that, suppose I fix the activity of gene A and gene B at x equals to 6. And now I ask you to give me an estimate or inference, estimation interval of the phenotypic expression. Then what you will do, you will have all your statistical machinery at your hand. You will use your linear regression technique because it looks like a linear regression framework. And you'll just point me to that blue point over there, that's my estimate. However, that's more of a statistical question that I've asked. Now let me ask a different question. Suppose I go inside the system and then forcefully intervene and then make the activity of two genes, gene A and gene B, forcefully to be 0. Now I ask you, what would be my inference interval for the phenotypic expression? So I want to hammer the fact that we need causality to understand this. So the next slide says basically that, suppose for the first scatter plot, suppose the underlying causal structure is that gene A has a causal influence to phenotype. So if I make gene A to be 0, then basically we would expect the phenotype expression to have an inference interval close to 0. Now suppose for gene B, my underlying causal structure is this. Suppose I have a hidden confounder that has influence both on gene B and phenotype. So if I make gene B to be, the activity of gene B to be 0, even then, since I have a clear causal direction from confounder, this hidden variable, we would expect the phenotypic expression to be somewhere around this interval. So it's not zero, it's not close to zero. So basically, what I mean to say is that we need to ask causal questions to understand the underlying structure in a more structured way. But I must say that our focus of the talk is the other way around. It's like here I am giving you this causal structure, and then you are trying to provide some inference. But I'm trying to do a inverse problem. Like what I'm saying is that I have some observational data in my hand. I have data in my hand. I want to discover the underlying hidden causal structure from that data. So this is what causal discovery is all about. This is what my advisors do. Yeah. And so this slide basically it defines what causal discovery is all about. As I said, it infers causal structure from data. Now, the gold standard to do this causal discovery is randomized control experiments. However, due to lack of resources, or the resources might be costly, it's not a very like we cannot obtain data from those experiments. So what we all have in our hand is observational data. And since observational data, it suffers from selection biases, confounding bias, its proper representation for causal discovery from that data is kind of very difficult to attain or to achieve. So it's a fairly difficult task to do causal discovery from observational data. So people, scientists from, I think, starting from 1920s and then again 1990s, they have leveraged this difficulty by introducing some assumptions to make this task more manageable. Some of the assumptions that I have stated are the causal Markov condition, causal faithfulness condition, causal sufficiency condition, and acyclicity. I wouldn't go deep into the meaning of those assumptions, but let me briefly describe what I mean to say about those. So suppose x1, x2, xp, it's the p nodes that I have of a graph. It forms a graph G. Our goal is to learn the graph G from this data that we have in our hand. So what causal Markov condition it says is that, say for example, I have this graph, like smoking has an effect on tissue damage, and tissue damage has an effect on lung cancer. So if my variable of interest is lung cancer, then if I have information that my tissue is damaged, then smoking doesn't provide any additional information on me having lung cancer or not. So basically, conditioning on the direct cause tissue damage, lung cancer and smoking are independent. And this kind of topological property of the graph, it goes to the stochastic property, like the joint distribution of the underlying nodes. So this is like a causal Markov condition. It says that our joint distribution has some sort of, the graph and the joint distribution, they speak to each other, in other words. Causal faithfulness is the other way around. It says that if for a certain joint distribution, we have some conditional independent states that it satisfies, then my graph will also have similar kind of things shown on the graph. So basically, it's the other way around. Like we go from the joint distribution to the graph, while causal Markov condition is like from the graph we are coming to the joint distribution. It's two ways. Causal sufficiency is that for a causal sufficiency means that people often assume it like to have that we don't have any confounders in our system. So we say that the system is causally sufficient. It helps our causal discovery task to be more manageable, and people have done that. We have also done that. Yeah.
So independence, where is the subscript of P?
Oh, it's like that's the subscript with respect to like the joint distribution. Independence with respect, and that's G is with respect to the graph. On acyclicity, it's like people have used DAGs. I think it's very popular, directed acyclic graphs, to assume that the underlying graph is a DAG. It's more easy to visualize, easy to handle. I'll explain a bit more on why it's easy in a few slides. Now, there are two major approaches that people often take in causal discovery. One is model-free and another one is model-based approach. So let me describe a little bit about model-free approach. It basically uses conditional independence tests to discover the underlying causal skeleton. It performs the tests like if X, Y, and Z are 3 variables. It performs tests like whether it asks questions like if X is independent of Y given the information of Z. So this is a non-parametric approach because we don't assume we don't have any distributional assumption. And the assumptions that these approaches often make are the causal Markov condition and causal faithfulness condition. But there is a problem, I wouldn't say it's a problem, but this kind of approaches determines the skeleton up to a Markov equivalence class. Now, what is a Markov equivalence class? So suppose these 3 graphs forms a Markov equivalence class because these 3 graphs expresses same conditional independence relation, that X2 is independent of X3 given the information of X1. You can think of that the smoking, tissue damage, and lung cancer. If we know tissue damage, which is X1, then smoking and lung cancer, they are independent. So these 3 graphs entail the same conditional independence. So we cannot uniquely identify the graph. Some of the examples of algorithm which has this model-free approach are PCF algorithm, FCI algorithm, and CCD algorithm. Now the question is, can we do better than this? By better, I mean, can we uniquely identify the graph? So here comes the model-based approach. So it introduces some sort of structural equations on the variables of interest. This is called a structural equation model. In the left-hand side, we have the variable xi, and the right-hand side, we have a functional model which takes in input of the parents of the variable xi, as well as a noise term epsilon I. This is a parametric approach because people often make distributional assumption on epsilon I. And so the main idea was to provide a model which is identifiable, or graph which is completely uniquely identifiable. So people have restricted the function class as well as introduced some with some additional distributional assumptions. It can be shown that the causal model is fully identifiable or uniquely identifiable. There's only one graph in that Markov equivalence class. Some of the examples are Lingam, Ling, linear non-Gaussian additive noise model. PNL is post-nonlinear model, nonlinear additive noise models, etc. But for our talk, we'll mainly focus on, we'll linearize this functional, we'll restrict our talk to linearizing this functional class to this linear in parents of X and the disturbance term or the noise term epsilon I. Now let me, before my main talk, I would just like to briefly describe what we mean by what does Lingam do. In order to do that, Lingam draws its motivation from independent component analysis method. So I'll briefly describe what an independent component analysis method is. So suppose there are 2 speakers who are speaking over a microphone, and there are 2 of us who are standing here, and we are listening to that. So when they're speaking, what I hear is a mixture of their signals. So this thing basically mixes this signal components S1 and S2. So what we observe are X1 and X2, which is like a linear combination of S1 and S2. There are non-linear variant of that. I'm not going into that. What I'm saying is just the linear combination of S1 and S2. For our goal of ICA is to recover these independent source signals S1 and S2 from by doing some method. There are algorithms for that. So basically, this is modeling. X is my observed. A is the mixing matrix, which mixes the independent components or the single components S. It's a linear model. Linear in it's just a linear matrix. Like yeah. Now I'll briefly describe the connection between IC. Yeah.
The dimension of S and dimension of X are the same.
Yeah. For our case, they're same, but there are cases where you can consider that signals are more than like the observations. They are called over-complete case or under-complete case based on your. But for us, we just need that those 2 are same in terms of dimension.
Is there any requirement like how many parents one node can have?
No, not really. That's what I said. Like it can be over-complete case. Like where number of signal components can be more than the number of observed values. So in that case, A wouldn't be a square matrix, it would be a rectangular matrix, a fat matrix or a tall matrix based on your assumption. It's overcomplete or undercomplete. It's the notions. So let me relate ICA and Lingam. So in ICA, as I said, I'm modeling X equals to AS. So our goal is to estimate this unmixing matrix W, which is inverse of this A mixing matrix. Similarly, in Lingam, if we write the model more compactly by linearizing the structural equation model, it would look like this. In Lingam, we strictly assume that the underlying causal structure is acyclic, that we have DAGs. Our goal is to estimate this B matrix. We call this matrix a causal effect matrix. So it's pretty similar. See, if I minus B is just W over here. So if we could correctly estimate W, then B hat is just I minus W hat, right? So it's a correct, like a very nice correspondence between these two theories. So under certain assumptions, people have, I think beginning 1990s or at the end of 1980s probably, people have started to prove identifiability of ICA models. So what they have done, they have assumed that the independent components are mutually independent, or the signal components are mutually independent, and they have some sort of non-Gaussian distribution. Under this assumption, this model can be made identifiable up to scaling and permutation indeterminacy of the signal components S. As you can see, this X can be written as A times P times D and D inverse P transpose and S, where P is a permutation matrix and D is a scaling matrix. So if we club this 3, we have A star, and we have, if we club this 3, we have S star. So basically it's an equivalent representation of our model. So the our model doesn't, it's not identifiable, right? And they have several algorithms that leads to efficient estimation of W. Now I must mention that although it's not of great importance in ICA, this source components or source signals, due to the presence of this permutation matrix P, they are not correctly ordered, right? So you cannot establish correct correspondence between X and S due to the presence of this permutation matrix P. But for Lingam, or to the methods that deals with causal discovery, you need a correct correspondence between this noise term E4. The noise term is basically equivalent to the signal component A star over here. So we need a correct correspondence between E4 to X4, E2 to X2, and so on and so forth. So unlike ICA, the correct correspondence between EI and XI is important in Lingam. So that's a major problem that ICA has, which the paper by Shimizu in 2006, they solved the problem by giving an algorithm for that. I'm not going into the algorithm, that's a totally different talk. It might take a full lecture, but so they have certain similar assumptions that EIs are non-Gaussian and mutually independent as the SI components over there. They do some sort of pre-processing on the W hat, on the W matrix, the estimate of the W that we get, and then they say that what they are giving, it's correct. It's correct. So this is how Lingam proceeds. Now, up till now, I've said that my underlying graph is acyclic. As I said, acyclicity makes causal discovery task more manageable, more easy. Now I'll briefly describe why is it so. So next, so consider this directed acyclic graph. It's a DAG. There's no cycle present, you can see. So if we have a DAG, we can have a corresponding topological order. What we mean by a topological order, I'll explain. So basically, if we consider these nodes as just some tasks, like task 1, task 2, task 3, and task 4, and if edges are the constraint that task 1 should follow task 2, then, and if we rename this as rename these variables as y1, y2, y3, and y4, if we draw equivalent representation of this particular DAG, we'll see that the causal direction will flow unidirectionally. This is a topological ordering. By topological order, we mean that if yi influences yj, then the subscript j should be greater than I. As I have renamed, in this example, I've renamed x2 to be y1, x3 to be y2. And you can see that the diagram here follows that it has like a causal direction in a particular direction, right? So under this assumption, if we write the structural equation model, the B matrix, it becomes a lower triangular matrix, or it can be made to be a upper triangular matrix. Okay. And now why is this helpful? If I take this matrix to this side and form the matrix I minus B, we have 1 in the diagonal elements. So I minus B is always invertible, right? So you can write the joint distribution of X in terms of the joint distribution of the noise variable easily for a cyclic case, right? And now suppose I have a cyclic graph. See, I've just flipped this edge and I have a cyclic representation. Now, what's the problem? Because if we have a cyclic graph, then there is a feedback loop. So suppose x1 influences x2, x2 influences x3, then x3 again can influence x1. So you cannot write that in that form. In that form, you cannot write that in that form. Causal direction cannot flow in that direction. You will have an arrow pointing backwards. So it's not like a topological order. You cannot have a topological order when you have a directed cyclic graph. So now if you write a structural equation model, then this B matrix cannot be made to be with a lower triangular or upper triangular matrix. You cannot permute the columns to get a lower triangular or upper triangular matrix. And this is a problem. And why is it a problem? If I take the B matrix to that side and suppose I calculate the determinant of the matrix I minus B, it's this quantity, right? Now, suppose I choose this 4 causal weights, to the product of these causal weights to be equal to 1, then this determinant is 0, right? And this makes that I minus B cannot be made invertible. So you cannot write X in terms of the distribution of the noise variables E, right? So therefore, people, they are always assuming something. And this is some conditions that people often make on B matrix to ensure identifiability. They assume that the moduli of the eigenvalues of B are less than 1 and none are equal to 1. So this is basic linear algebra. If eigenvalues are less than 1 and none are equal to 1, none of the real eigenvalues are equal to 1, then the eigenvalues of I minus B strictly lies between 0 and 1, which makes the I minus B matrix invertible. And now you can go and you can associate your thing with the directed acyclic graph. As I said, like X can be written in the form of the joint distribution over this noise variable E. So I have said the challenges of having cycles, as well as with that assumption, I have said that you can manage that challenge. Now let's start with my talk. It's main part of my talk. Enough of background. So let me define what a functional data is. So functional data are data points which are itself functions or curves. So if we define it more mathematically or more formally, it's a realization of a random object that takes values in an abstract function space. And the example of an abstract function space can be a Hilbert space. Hilbert space. You can take your any favorite abstract function space. Now, suppose I have p random functions, and I can stack it and make it a vectorized form, and this gives me a multivariate functional data. So here X is multivariate functional data, where x1 up to xp, they are each random function. Now, example. The first example is an example of a functional data. It's a daily particulate matter. It's a air quality control thing. So it's a daily particulate matter of size 10. Concentration curves are recorded in a place called Graz in Austria in winter season. So every sample point is a curve or a function. You might be interested to know the mean curve or something like that. This mean is the one which is bold. This to draw inference, but that's not our goal. And another example of a multivariate functional data is what we have considered in our paper too, is the electrical activity which is measured across different regions of the brain. And people are often interested, and since the electrical activity in the different regions are measured at the same time, so you can consider it as a multivariate random function. Now, as I said before, that there are some challenges to do causal discovery from multivariate functional data. So some of the challenges are outlined over here. So first challenge is it's not specifically related to multivariate functional data, but as we know that since the data points are itself functions or curves, they are infinite dimensional, right? Now, so for infinite dimensionality, suppose it might happen in causal discovery, like a high frequency spectrum of a curve might causally influence a low frequency spectrum of another curve. So you want to have you want to identify some relevant features which helps to keep the all the causal information in some sort of low, which gives us some lower like a representation of a lower dimensional space. But the challenge is you wouldn't know a priori what those relevant features are. The second challenge would be like causal identifiability theory to prove that your model is identifiable in multivariate setup. I'm not talking about multivariate functional data. Even in multivariate setting setup, it's very difficult in presence of cycles. So now you're talking about multivariate functional data, you have infinite dimensionality, and that's a huge difficulty which we have kind of addressed in our paper. And the third level of difficulty is you don't observe functional data directly. What you observe are some sort of noisy functional data, and this presence of noise adds another layer of difficulty in probing the causal relationships of interest. Now, it's a motivating example, as I was saying. This is a easy data where a person, you can see a person who has these are called electrodes. They're in international. It's a rule that you put 64 electrodes on your head or a brain. You can put it on your scalp or just over the brain, and you measure electrical activity from all those regions. Since the measurements are continuous and the interval of observation, like the measurement interval, is short, there's a short time separation, then it can be considered to be a multivariate random function. People are often interested to understand like how a particular region of the brain might causally influence another region of the brain. So these are all called brain effective connectivity studies, and we are also interested in this in this paper. So far now, what people have assumed is in the brain regions there are no cycles. Everything is acyclic. It's beneficial for them to do modeling, but that's not true in the real world. So we have evidence from biology literature which says that there are innumerable number of feedback loops or cycles in the brain. So our goal is to model causal relationships in the brain network in presence of those cycles. Now let's come to our proposed model. How are we modeling this? So consider a multivariate stochastic process Y having P nodes. I'm calling it node, but it's just the random functions Y1, YP, Y2, and YP. Each node is my random function. And Yj belongs to some Hilbert space Hj. And the domain of definition for Yj is Tj. It can be a time component. It can be a spatial component. For our motivation, since we are considering electrical activity, you can think about it as a time component, but in other applications, it can be a spatial component. So we are not restricting it that, we're just calling it as some location Tj. It can be a time or spatial. So we consider an operator-based linear structural equation model on Y, which looks like that. It's kind of familiar to what we have already seen before. Why are we saying this as an operator? Because this is a random function. So we have to make this thing also a random function. Left-hand side and right-hand side should match. So that's the reason why BJL, which is a causal effect matrix, as I have defined before, it's an operator. It takes in YL, which is a random function, and outputs inputs are function. So basically, it makes everything regular. Left-hand side and right-hand side both are random functions. So that's why we are saying that it's an operator-based structural equation model. Now, if we have a causal effect from YL to YJ, then it basically says that that particular entry BJL is a non-null operator. It's not equal to 0. And we assume in our model there are no self loops. That is, a particular vertex cannot be a parent of itself. So BJJ is strictly a null operator. It's 0 for our case. Now, to draw relation to the usual multivariate setting that we have seen, we usually see, we can assume that Yj, suppose if Yj belongs to some Rm, then we can equivalently write this as a structural equation model where this BJL is basically a matrix. Here it's an operator, but this becomes a matrix, a finite dimensional matrix. So it's just to draw a relation between the usual multivariate setting, but for a multivariate, for a functional setup, you have all infinite dimensionals involved in this particular model 1. So it's not good to write it like this because it's infinite dimensional in nature. So model 1 is, as I've mentioned here, it's infinite dimensional. So it would be challenging to estimate and as well as interpret this model. So now we have done something to alleviate this difficulty. We have assumed that the causal relationships that we are interested to know about, they lie in a lower dimensional subspace DJ of 8J, which we are calling it as a causal embedded space. All my causal information are located in that space. It is a finite dimension KJ. Now, that's our assumption. And then we are saying that if PJ, that PJ and QJ are the projections of YJ on DJ and its orthogonal complement, respectively. This is basically a mathematical formulation of saying that BJL is PJ times BJL times PL. It's mathematically way of saying that the causal effect matrix lies in that lower dimensional space that we are considering. It's just a mathematical expression. We don't need to worry about that. And as such, under this assumption, our model 1 that I have defined here can be split up into 2 parts. This part involves all my, this is a structural equation model because as I've said that PJYJ is a projection into that space that has all the causal information in it. So basically this is a structural equation model on that space. And this one is a noise. And we are saying that this projection doesn't have any causal information. So we are assuming that the error terms of the noise variables QJ, FJ, and PJ, FJ, they are independent of each other. They just don't interact. We're just assuming that. Now, in practice, we do not observe, as I think I have mentioned before, that we do not observe functional data directly. It comes with noises. So for our case, for each YJ, we observe a location TJU and XJU, where XJU is the value or the measurement of YJ at that location TJU. So this gives us a measurement model given by 3, which is XJU has an additive model in YJ, which evaluated at the location TJU. It's a functional data and it's a functional form, and EJU is just my noise term. And this YJ has 2 components, PJYJ, as I mentioned, because you can split up it into 2 components. And I have assumed that the independent noises has some normal distribution. So recall that this is my measurement model. This is just a summary of what we are doing in our modeling setup. This YJ and EJ, they are affecting the, I'm not saying it's like not like causal affectedness, just like to pictorially depict what I'm trying to say, that XAU is our observed value. So it consists of those 2 terms, YJ and EJ, and YJ can be further split up into 2 parts, PJYJ and QJYJ, where PJYJ has all the information that we are interested to know about, and this is devoid of any causal information. Yeah. So if I define is alpha j as pj yj, beta j as qj yj, then more compactly, this thing can be written as model 4. Now we are interested like to now one might ask like, if is your proposed model causally identifiable? I must assure you it's identifiable because we have shown it under certain assumptions it is identifiable. Otherwise I wouldn't have given this talk. But so yeah, so yes, under certain assumptions. Now let me describe like the standard assumptions that people often take. So one assumption is causal sufficiency. We have seen this assumption before. It says that my system is devoid of any confounders or the latent hidden causes. This keeps the causal discovery task more manageable, especially for cyclic graphs from purely, if we have pure observational data. A second assumption would be like, this is a disjoint cycle assumption, which says that the cycles in this graph, in a graph G, are disjoint. That is, no two cycles in the graph have two nodes that are common to both. Let me describe this to you with the two graphs that I have. Consider this right-hand side, the graph that is right-hand side. I have two cycles, x1, x2, x3, x4, and x1. And I have another cycle, x1, x2, x3, and x1. There are two cycles and they do share two common nodes, x1 and x3. We are not allowing such structures in our graph. What we are allowing is this kind of structures where you can clearly see there are complete separation between two cycles. This x1, x2, x3, x4 form a cycle, and x5, x7, x6, they form a cycle, and they do not have any nodes that are common in both of the cycles. So we are allowing for such structures. I will not describe the proof or technique of causal identifiability that we have in our paper, but this helps us to keep our proof technique more manageable. And yeah, and the third assumption is the stability assumption we have seen before, like the eigenvalue condition that we impose, that it is less than, or the eigenvalues of that finite rank operator B are less than or equal to 1, and none of the real eigenvalues are equal to 1. It's a similar extension to what we already discussed in the univariate setup. This is my third assumption. The fourth assumption is the distributional assumption, because we are considering parametric approach. So we have some sort of distributional assumption in our method. So we assume that by exogenous variables, we mean the noise component in the structural equation model. So they have some sort of like mixture of normal distribution. Now one might argue, why are you taking a mixture of normal distributions? So basically, it has been proven in literature that if you have large number of mixture components, it can well approximate any continuous distribution. So it's not bad to assume this, I must assure you. And this is also inducing some sort of, it has also like the methods where this assumption has induced model identifiability in the univariate setup. So we kind of use that fact for our model too. This assumption, it's more like this beta j component is my component which doesn't have any causal information. So what this assumption says is that although it has temporal dependency within a block of beta j, there's time dependency, but beta j is independent of beta L. If it is not, otherwise what would happen? Because suppose it has some sort of, if it has some sort of causal information, then you could say that there is some sort of dependency between beta j and beta L. But since we are saying that there are no causal information, it's good to assume that beta j and beta L, they are independent. So it's what's all this assumption is telling us. And this is an assumption that we have. It basically says that we have enough sampling locations over which each random function yj is observed, so that the relevant causal information that is hidden in yj, we can capture all those causal information. So basically it says that this basis matrix K phi t, which I have defined over here, it's a tall matrix. Here mj is the number of observation points. So here mj, the summation over mj and summation over kj is the dimension of the causal embedded space. It says that just that K5 matrix is a tall matrix. We have enough sampling locations because this mj is the row one, so it's like a time component. So it's a tall matrix. Yeah, so that's what this assumption basically tries to say. Now this is like a summary of all the assumptions. We have 6 assumptions: causal sufficiency, disjoint cycle, stability, non-Gaussianity, non-causal dependency, sufficient sampling locations. Under these 6 assumptions, we have shown that our model is causal identifiable. What we mean by causal identifiable, it's that no two graphs entail the same joint or gives us the same joint distribution. So under these 6 assumptions, we have proven the identifiability of our model. I'm not going into the proof because, and you can check it from our paper that has been uploaded in the archive now. Now I'll briefly describe the model parameters of interest that we have. It's more of an inference problem. So this E is an adjacency matrix where EJL is 0 if there is no directional influence, and it's 1 if Yj influences Yl. And this is a measurement model. This sigma j parameter of the noise term, variance parameter, is also our parameter of interest. Now, suppose we approximate this random function Yj with some unknown basis function phi k, expand it with respect to unknown basis function phi k, and here S is some large quantity S. And then we need to keep in mind that phi k is not those basis functions which spans the causal embedded space that we are that are of interest to us, but we are assuming that the first kj components of this structural equation model is the spans that causal embedded space. So we define the structural equation model on the first kj components of this expansion, as you can see over here. Now, since phi k's are useful for restricting each yj to that lower dimensional space dj, these phi k's are very useful to restrict each yj to dj, but we don't fix them, or and they are not like just the principal component, or it's not functional principal component analysis happening over here. We just try to choose phi k more data adaptively. It's like an adaptive basis expansion approach where we further expand phi k with respect to some known cubic B-spline basis functions given by this equation. And so we define a prior, we have a prior over this basis coefficient AKs, and this helps us to choose phi k's more data adaptively. And this is the parameter, like this is the noise variable in this ACM structural equation model. I should have put a tilde, but yeah, I missed it. So it has a mixture of normal distribution. The mixture weights, the mean variable and the variance variable are all of our parameters of interest. So I'm not going into the prior specifications, some very standard priors are taken to formulate our Bayesian procedure. Now let's go describe our simulation setup. So we have considered sample sizes for 75, 150, and 300. And the number of nodes, like the number of random functions, are 20 and 40. And the number of time points over which each random function is observed is fixed at 125. So the causal graph G is estimated by thresholding the posterior probability of inclusion at 0.5. It's basically estimating that E hat. G is basically, it's just E hat. Now we have compared our methods against 4 methods. The first method is a method by one of the previous students of Young, Fang Ting, Joe, if you know her. But their model deals with acyclic case, but it's developed for multivariate functional data. And due to the lack of other existing methods for functional data, we had to resort to some 2-step procedures, which are 2-step methods, which are given by 2, 3, and 4. So what we do is the first step, we obtain the basis coefficients by carrying out functional principal component analysis for the random functions. And then using those basis coefficients, we try to estimate the causal graph using some existing causal discovery methods. This is a 2-step procedure that we are having. We compare our method against this. the name of our method is fence. I have, yeah, it's mentioned over there. So we have used Matthews correlation coefficient. It's a very robust measure to assess the graph recovery performance. It lies between -1 and 1. So a value of 1 means perfect recovery. 0 means it's similar to random guessing, and -1 it's horrible. Then so the thing is, we are performing, as all simulation studies say, we are performing better than all other methods. So why is it, and why is such stark difference? Because although this Fling method is developed for multivariate functional data, but it has inherent assumption that the underlying graph is acyclic. So, but we have cycles in our simulation studies. We have developed. It involves cycles. So there are many false discoveries, as well as it cannot discover many stuffs that's going on. So it's around 40%. And other three methods are pretty less. I must mention that this FPCA CCD, the CCD algorithm deals with cyclic graphs. But since this is like a two-step procedure, the causal information doesn't flow nicely from the first step to second step. And that's the reason why they are underperforming. So this is all about our results. And then there is an application that we have done. As I was saying, we have considered 122 subjects. It's an alcoholic study where among them 77 are alcoholic patients and 45 of them are control patients. So we want to study how their brain connectivity, how the alcoholic group's brain connectivity differs from the control group's brain connectivity. So this belongs to the alcoholic groups. This is our model. This is based on our model. This is the brain structure or the corresponding to the alcoholic group, and this is for the control group. For both the groups, alcoholic and control, we have found out that the brain regions that are spatially contiguous, they tend to be more connected. See, these are bidirected edges. By bidirected edges, we assume that there is an causal influence from, suppose for F3 and F1, there's F3 influences F1 and F1 influences F3 again. So it's like a cycle of length 2. And dense connectivity is observed in the frontal region of the brain in both alcoholic group and the control group. And there's another observation that alcoholic group has more connectivity across the left parietal and occipital lobes. Now, I assure you that our reviewer from New Riffs asked us how is it valid findings. So we had to carry out some sort of biology literature survey, and we have found out that this sort of findings are not random. They validate what we already have in the biology literature, and so our method can validate what the biologists have already said. So yeah, and this is our application on this real data set EEG. And so now some key takeaway messages, what I've done at the end of my lecture. So we have proposed an operator-based linear structural equation model based framework for doing causal discovery from multivariate functional data. We have introduced a notion of existence of a lower dimensional space which captures all the relevant causal information. And we have proved the causal identifiability of our model under certain assumptions. These are fairly difficult tasks to do, but we somehow achieved it through this paper. And we showed applications over an EEG dataset. Now, some future directions would be to relax the assumption for causal sufficiency. People often say that's my future direction, but they don't proceed because it's very difficult to proceed. But yeah, that's how I also mentioned that we want to relax, but I don't know whether I can relax or not. And another one is to consider a nonlinear ACM framework. That's another difficulty, another level of difficulty. Probably will take. I'm doing something related to nonlinear ACM, but for the univariate setup, not for the functional data setup. I don't know. Maybe at the end of the PhD, like fifth year, maybe I could come up with something. I'm not sure about that. And yeah, this is end of my talk, and this is my paper, which has been recently accepted at NURIPS 2023. And this is the thing that you can scan and get the archive version of my paper. And thank you.
So how do you go about, or do you go about identifying the non-causal part of the data?
That's a nice question. In order to say that, I need to say a lot about, I kind of swept under the rug for the in the inference part that I've said. Maybe we could talk later because I need to say a lot about that. So maybe we could talk later if you are available to talk. Yeah, but I can't say it in just. Yeah, so very sorry, but yeah. Yeah, please. Yeah.
I was just wondering if like model based.
Yeah.
Questions would have like multiple predictors.
Yeah.
Do you just assume all of them have like some kind of cycle to them? Or like
Not necessarily. Not necessarily. There might be cycles from particular exercise, but I mean, it's not likely that all of your variables will have those cycles. But yeah, that's not the assumption. Yeah. Yeah, please.
Quick question, I probably missed something, but you're using mixture Gaussians to approximate something that's non-Gaussian, but the mixture weights could still lead to something that's either Gaussian or very close to Gaussian. Is there something in, does that matter, or is there something in there?
So basically, what we took the particular form of this mixture of Gaussian because it helps us to prove causal identifiability.
Sure.
I mean, yeah, I mean, it might lead to.
When you estimate the model, it could end up with something. Okay.
Yeah. Exactly. So.
And then for the temporal part,
Yeah.
just to follow that, you're encoding most of the temporal to the functional way, so it's kind of a function plus the IID.
Yeah.
There's no autocorrelation for errors or anything like that.
No. They're independent. They're independent.
Is
No.
that gonna matter, right? Can we add that in somewhere?
Yeah, because if the noises are correlated, then it basically means that we are out of our causal sufficient system.
He's talking about like the process.
No.
Process different.
Oh, the process they have correlation. Oh, I'm sorry. Yeah. Sorry. Yeah.
It's something I missed.
I'm sorry. Yeah. Okay. Sorry that I couldn't understand the question. Sorry. Yeah. Sorry.
Good.
right? Thank you very much again.